Okay, let's look at some review problems that deal with some of our analytic and some of our trig from chapters 8. So the first one says, what's the cosine of 7 pi over 12? So if I was ever given a problem like that, the first thing I would do is probably switch it to degrees. So I have 7 pi over 12 times 180 over pi. So the pi's cancel. So 180 divided by 12 is 15. So we're talking 7 times 15. So that's going to equal 105. Now 105 is obviously not on our unit circle. So this is one where we'll have to use our sum and difference formula because I do know 105 is 45 plus 60. Now on your final, all these formulas are given to you, so not something you really have to memorize. But the cosine of two angles added together is the cosine of the first times the cosine of the second minus, it's always the opposite sign, sine of the first times sine of the second. And now all these things, all these angles, 45 and 60, are on our unit circle, so they will be okay to be used. So the cosine of 45 is radical 2 over 2. The cosine of 60 is 1/2. Minus, now the sine of 45 is also radical 2 over 2. And the sine of 60 is radical 3 over 2. So when I simplify these, radical 2 times 1 is radical 2 all over 4 minus radical 2 times radical 3 is radical 6 over 4. So I could just leave it as radical 2 minus radical 6 all over 4. So for number 2, it says, what is the inverse sine of negative radical 3 over 2? Now, this is one that you could put in your calculator. But remember, the inverse sine is going to give us an angle, and we know two things about that angle. We know the sine of that angle is equal to negative radical 3 over 2. And so on our unit circle, there are two places where sine is negative radical 3 over 2. But I also know that theta has to be between pi over 2 and negative pi over 2. So if I look on the unit circle where that is, I see that on the unit circle at 5 pi over 3. 5 pi over 3 has the point 1/2 comma negative radical 3 over 2. But 5 pi over 3 will be the incorrect answer because it has to be between negative pi over 2 and pi over 2. So if you think of 5 pi over 3, that's the same angle as negative pi over 3, coterminal anyways. So negative pi over 3 or negative 60. So if you were in degree mode, it would really just kind of give you what that is as the degree, but same as the radian. All right, let's look at number 3. Number 3 is a very popular problem to put on finals, where you have the sine of the inverse tangent of 3/4. So again, let's start with the inside. We know the inverse tangent of 3/4 is some angle theta, and I know theta, tangent of theta is going to equal 3 over 4. And I know theta has to be between pi over 2 and negative pi over 2, quadrant 1 or 4. This is true for sine and tangent. The only one that's different, remember, is cosine. So what I would do with this problem is I would draw a little triangle. And I know the tangent is 3/4, which is opposite and adjacent. So the opposite is 3 and the adjacent is 4. So obviously I could use Pythagorean theorem, 3 squared plus 4 squared equals c squared to find the hypotenuse. C would equal 5. And so now what I want to do to finish this problem up is I want the sine of this angle. So I just use this triangle. Sine is opposite over hypotenuse. So my answer would be 3/5. Okay, so let's look at the next three problems, and they all have to do with this precursor that says given the sine of beta equals 5/9 with beta between pi over 2 and pi, find the following. So again, a very kind of typical problem where they give you one triangle and you have to answer a bunch of things about it. Well, I know the triangle's in quadrant 2 because here's pi, or the angle's in quadrant 2, so pi over 2 and pi. So here's my reference angle beta for my reference triangle. And I know sine is 5/9, so opposite is 5, and hypotenuse is 9. And so then I'll just find the other side, 9 squared equals 5 squared, plus this x squared side. So that's 81 equals 25 plus x squared. I will subtract 25 and get 56. And then I'll take the square root. Now the square root of 56 can be simplified because it's 4 and 14. So it will be 2 radical 14 equals x. But that's actually not going to be my side. My side is actually going to be negative 2 radical 14 because I'm going backwards in quadrant 2. So now that you have this, you can use your formula sheet and really solve all these problems. For example, the first one says, what is the sine of 2 beta? Well, from my formula sheet, it says the sine of 2 beta is 2 times the sine of beta times the cosine of beta. Well, I know the sine of beta is 5/9, and I know the cosine of beta is adjacent over hypotenuse, so that's going to be negative 2 radical 14 over 9. And then this is 2 over 1. You can just multiply the tops and bottoms. So that's going to be negative 20 radical 14 all over 81. So the key thing is to set up a triangle and then use your formulas. So the second one says, what's the tangent of 2 beta? Well, the tangent of 2 beta is given by the formula 2 tangent beta over 1 minus tangent squared beta. Well, then I need to know what tangent beta is. Tangent beta is opposite over adjacent. So that's going to be 2 over all over 1 minus 5 over negative 2 radical 14 squared. So we got a little bit of simplifying to do here, obviously. I can cancel the 2 with that 2. So that's going to give me negative 5 over radical 14. And on the bottom, I'm going to get 1 minus 25, because 5 times 5 squared is 25. And on the bottom, I'm going to get 4, because 2 squared is 4, negative 2 squared is 4, times 14. Because when I square the 2, I get 4, and when I square a square root, the square root just goes away. So that's going to be negative 5 over 14 all over 1 minus 25/56. I can then just subtract the fractions. What is 1 minus 25 over 56? That's going to be 31 over 56. So negative 5 over radical 14. Got the radical on this one. Over 31 over 56. Then I can just flip it, do the old flip and change. So it'll be negative 5 over radical 14 times 56 over 31. So that's going to be negative 280 over 31 radical 14. And you could rationalize if you want just by simply multiplying top and bottom by radical 14. But I'm just going to keep it like this. Okay, let's look at our last one. Our last one is the cosine of beta over 2. Now, interestingly enough, if you remember the formula for the half angle, it's going to be plus or minus the square root of 1 plus cosine beta over 2. Well, I know from my triangle that the cosine of beta is going to be negative 2 radical 14 over 9. So that's not a problem. The thing that is somewhat tricky is it plus or minus? Well, let's think about it. Our angle is between 90 and 180. I know it was in radians, but I'm just going to put it in degrees. So if I think about what half of that angle is, then the half angle beta over 2 is between 90 and 45. So that's somewhere in quadrant 1, so I know it's going to be positive. So we have positive square root, and it'll be 1 plus the cosine, which is negative 2 radical 4. over 9 all over 2. And the only thing I'd really simplify is I'd probably multiply everything by 9 just to clean it up a little bit. So that would leave me with 9. Well, it's plus and negative. I could just put minus 2 radical 14 all over 18. That'd be a fine answer. So the next couple will talk about some trig equations. Remember, our goal is to get the trig value by itself, and then we'll try to use our unit circle to find the value. So for this first one, I can simply just get the sign by itself by adding 1 to both sides and then dividing by 2. So we're trying to find the answers in the interval 0 to 2 pi. So on my unit circle, I'm looking where is the sign value or the y value on the unit circle equal to 1/2. And I know if I look at my unit circle, then the two places where sine is half is at pi over 6 and 11 pi over 6. So those would be my two solutions, pi over 6 and 11 pi over 6. Now, we know these do repeat. These are the ones in the interval 0 to 2 pi. But if I wanted the general solutions, I do know they repeat every increment of 2 pi, because as long as I go around the circle one more time, I'm going to get another solution. Now, the second one is one where you have to use your identity, and namely a Pythagorean identity in this case. So it says 1 minus cosine squared equals sine theta. So we know that sine squared plus cosine squared equals 1. So our rewrite would tell us that sine squared equals 1 minus cosine squared. To do any trig equation, you have to have the same trig function value. You can't have multiple ones. So this will become sine squared equals sine. And then I'll get everything on one side, because if there's a square, we're going to have to factor out. So we get sine squared theta minus sine theta equals 0. So I can factor a sine out, sine theta times sine theta minus 1 equals 0. And then I'll set those equal to 0. So I want to know where is sine theta equal to 0 and where is sine theta minus 1 equal to 0. And that's the same as saying sine theta equals 1. So I look on our unit circle, where is the sine value equal to 0? Well, it would be at a couple spaces. It would be at 0, and then it would be at pi, because the y value is 0. And it would also be again at 2 pi, because 2 pi and 0 really are in the same spot. So it makes sense if 0 is a solution, then so would 2 pi. Now, as far as where sine theta equals 1, that's where on the unit circle where the y value is 1, that only occurs at pi over 2. So these are my collection of solutions in the interval 0 to 2 pi. So our last problem here says verify the identity. This is where we have to use some of our trig identities to manipulate an equation to look like a new expression. So again, lots of ways to go with these. So if I was going to do this one, I would start on the left. And so if I look at the left, I see I can change secant to 1 over cosine times sine of x, because that's there. And on the bottom, I have tangent x plus cotangent x. So I really don't have much way to go with that. So I'm just going to turn them into their quotient identity equivalents, sine x over cosine x plus cosine x over sine x. Now, we did this several times when we did identities. When you have two fractions added together, we have to get the common denominator. So in this case, the common denominator at the bottom is going to be sine cosine. So I'm going to add a sine and a cosine to the top and bottom. So that's going to clean up to be sine x over cosine x all over sine squared x plus cosine squared x all over sine x cosine x. That's just putting the two rational expressions together on the bottom. But if you look, we have sine squared plus cosine squared, and we know sine squared plus cosine squared is just 1. So this is sine x over cosine x over 1 times sine x cosine x. So now again, we have the fractions divided, which we do quite often in these expressions. So we have sine x cosine x times sine x cosine x over 1, just because I'm multiplying by the reciprocal of the second. Well, you can see the cosines will cancel, and we're just left with sine x times sine x, which just happens to be sine squared x, which is what I'm trying to prove it equals. So just start on one side. I would say start on the side that has the most stuff and try to manipulate it till you get the other side. So that's all for review 2. One more review to go. Obviously, please let me know if you have any questions.